So today we're talking about inductance. We're in chapter 30. Inductance is going to look very, very familiar. Hopefully it's kind of pretty easy for you guys to pick up because it's basically Faraday's law all over again, just kind of with a different look on it. So all the same stuff that you learned from chapter 29 applies right in this chapter 30. The first topic here in chapter 30 is mutual inductance. Mutual inductance is this idea that if I have two coils in the vicinity of one another, just try and draw like some decent looking coils here. Here's coil number 1, let's say. And then I have a coil number 2. Maybe I'll change the color on it here. And in principle, these two coils could have a different number of turns. So let me just go ahead and cut that one off right there. That'll be our coil 2. When I run current through coil 1, like this, I'll just go ahead and use the lowercase I notation since the book is using that. If we run some current through this coil here, suppose the current is off and then we turn the current on, so the current is increasing, right? There'd be a magnetic field created inside of this coil. To avoid drawing too many lines, I'm just going to go ahead and just draw that central line, which is kind of perpendicular to the plane of the loops there. And that magnetic field would be increasing, right? And so we know that if you have an increasing magnetic flux in a coil where there was, there's no flux there before, and now all of a sudden you have a flux, then you're going to induce a current to oppose that flux. So we can see here that the magnetic field from solenoid 1 is going to make its way over to solenoid 2 and increase the flux. Let's maybe make a note here. So the change in flux here for coil 2 is going to be bigger than 0, right? It's increasing. And because the flux is changing, right, Faraday's law tells us that there's going to be an induced current, an induced voltage, an induced magnetic field, and so on. Okay. How much current will be induced in the circuit? Well, quickly, before we talk about that, let's go ahead and get warmed up with our right hands, because we can always use the right hand rule to figure out the direction. So if B is increasing in this direction here in solenoid 2, what is going to be the direction of the induced magnetic field? So that is a question for all of you. So what is going to be the direction of the induced magnetic field in coil 2? Let me go ahead and remind us that this magnetic field here is increasing. Excuse me. You can go ahead and just put your answer in chat when you get it. of one student direct messaging me the answer. Okay. Okay, we have two now, two answers. I am asking for the direction of the induced magnetic field, not the induced current here. I never asked for you guys to direct message me either. You can feel free to put your answer in the chat for everyone to see. It's fine. This is just our warm up here. Still less than half of us have given an answer, so. Okay, so now we can see some disagreement here in the chat. Always good. Maybe you can put your reasoning, try and convince others. So what will be the direction of the induced magnetic field in coil 2? Okay, now we're starting to see some reasoning here. That's good. See if anybody has some counter arguments. Anybody want to change their answer? Okay, well, the flow of the chat here has kind of stopped, so I think I'll go ahead and take it from here. To answer the question, we simply need to know the direction of the change in the magnetic field. Since B is pointing in this direction and B is increasing, the change is in this direction. So this would be a vector delta B. And Faraday's law tells us that, or rather Lenz's law tells us that the induced fields or the induced currents or the induced voltages always oppose the change. So if the change is pointing to the right, then to oppose that change, we must have an induced field which points to the left. That would be opposite to the change. Okay, so those of you who had to the left are correct. Remember, it's Lenz's law or Faraday's law. You always oppose the change. The induced anything opposes whatever's there already. The change in whatever's there already. Okay, so let's go ahead and now clean this up a little bit. So B is increasing, and that gives rise to an induced magnetic field over here in this coil. And then kind of based on how I drew this, I kind of drew it so that at the top, the current is going in. So current here, so you can find my mouse, there it is. So the current is going in this direction here like this. We'll call this one I2. I'll call this one I1. And now what we want to do is we want to get rid of, so to speak, the magnetic flux and the magnetic field and just talk about currents. And the reason we want to do that is because we're headed towards applications of these coils in circuits. And it just kind of makes sense to kind of get rid of this idea of magnetic flux and magnetic field when you're dealing with circuits, because when you're doing circuit problems, you're solving for currents, right? Or you're solving for voltages. And what we'll see is, we'll talk about an LR circuit, which is a circuit with a resistor and an inductor, which an inductor is basically just a coil of wire. And we'll solve for, a time-dependent current, just like we did for the RLC circuit, similar type of thing. So we want to just kind of get rid of the magnetic field and magnetic flux in our formulas and kind of rewrite them in terms of current. And it just makes circuit analysis a lot easier for us. So let's go ahead and do that now. We define a quantity called mutual inductance in the following way. What we do is we take Faraday's law, which of course everybody remembers at this point, right? The induced electromotive force is minus the number of turns times the rate of change in the magnetic flux. We simply rewrite this thing. And I guess I should be a little bit careful with my subscripts here, but let's just go ahead and refine the expression later. So we want to convert this equation over to one which looks like this. Something along these lines, where m again is a constant. M again is a constant called the mutual inductance. Now let's go ahead and add in some subscripts to this equation, because it's quite important that we have the subscripts to understand what the equation is saying. So constant mutual inductance. It is the coil 1 here, which has a current which was changing. So we started with no current, and we flip a switch and the current turns on. And so the current that's changing here and inducing a current in coil 2 is current 1. So di1 dt times the negative mutual inductance there. The minus sign is just from Faraday's law there. So times the mutual inductance with a minus sign. And that induces a potential difference or a current or a magnetic field in coil 2. So this is how the subscripts should look here. Now, oftentimes, and I think this is in your book as well, oftentimes you'll see this expression written down, something like mutual inductance from 1 to 2 or from 2 to 1. I'm going to skip over those, that portion of the section. So read that portion to convince yourself that the mutual inductance from 1 to 2 is the same as from 2 to 1. The book quickly does away with that. They'll just show you the two are the same and then quickly move on, and there's only one value of m. But here's something I will do. I will convince you that this m indeed is typically constant for a lot of materials. Not all materials, but it's typically a constant. To do that, simply consider this equation right here. So the flux is some integral of B dot dA, right? And we know from Ampere's law, that if we were to do an integral around a closed loop, the dot product between the magnetic field and the parameter that is along that path, dl, we get something like mu 0I, right? The current that's enclosed in that loop. And so what we see is that the flux depends on the magnetic field, and the magnetic field then depends on the current, right? And so maybe we can take a look at a simple case where the magnetic field is relatively constant. Now, in this case up here, that certainly wouldn't be true. The reason being because these two solenoids are, some distance away from each other, and the field on the outside of a solenoid is not very uniform at all, right? It's curling back around to the other side of the solenoid. But you could imagine, a situation where I have some coils of wire like this, and then I put another coil just right on top of that coil or inside of that coil, like so. I know this is probably a little bit difficult to kind of visualize, but imagine I have a coil kind of wrapped around another coil there. Now we know inside of a solenoid that the magnetic field is very uniform. It's like a parallel plate capacitor's electric field. So the magnetic field inside of a solenoid has magnitude mu 0 lowercase n times the current I. And it's very uniform inside the solenoid. So uniform inside the solenoid. Okay. And so if we were to change the current there and the magnetic field is uniform, then we wouldn't have to worry about too many challenges there with calculating the flux, right? Because the flux for those loops is just constant all along the loops there. And we wouldn't have to worry about any fringe field effects because the field is uniform. And so we can imagine, something like this simply becoming B times A, where A is just the area of one of those loops. And then, so this would be equal to the flux here. And then over here, we would see for the solenoid, we already know the answer, right? B is mu 0 n times I, which I already wrote down. You can just substitute this in over here, and then when you take a time derivative, the only thing that's changing there with respect to time is the current I, right? And so we can see maybe what M might be equal to in this simple case here. But my goal there was just to convince you that M indeed would be a constant. So collect all of the other terms besides the time derivative with respect to t. Excuse me, the derivative of the current with respect to t, and that would be what M is equal to. So I'll leave that as an exercise for you. So hopefully that convinces you that capital M is constant for most materials. When is it not going to be constant? It's not going to be constant when materials have what is it called again? Magnetic permeability that's not equal to 1. Okay, so if you remember, there's like a dielectric constant, right? And then there's like a magnetic constant as well. This one is called the permeability. Or magnetic permeability, I should probably say. Okay. So when you're dealing with materials which strongly react to magnetic fields, for example, like iron, you wouldn't expect a relationship like this to hold if you actually had iron wires instead of like copper wires. For copper wires, which is what we typically use, it's low resistance. It doesn't respond. It doesn't. It's what do you call it? Paramagnetic, not ferromagnetic. Iron is ferromagnetic, so it has a strong magnetic response. So for a material like iron, we would not expect a relationship like this to hold. Be a little bit more complicated. Okay, so just to quickly reiterate here, I mentioned this already, but let me just reiterate. So in some cases, you'll see this expression written down with 2 subscripts on the M, but your book will show you pretty quickly that indeed it's the same mutual inductance for the same 2 solenoids. So you take 2 solenoids, you put them next to each other, there's only 1 mutual inductance. Okay, so now I will give you a problem I already said I would leave as an exercise for you. Let me just make things easy on myself and copy it from the book here. Actually, maybe it would be better if I grab it this way. I'll just type this out so I can make it bigger. In one form of a Tesla coil, a high voltage generator popular in science museums, a long solenoid with length L and cross-sectional area A is closely wound with N1 turns of wire. A coil with N2 turns surrounds it at its center, kind of like I mentioned before. Up here it's got to be wound around the center so that B is uniform. Find the mutual inductance for this 2-coil system. Okay, so for this problem, I think maybe I'll put you guys in groups on this one to work on it with a partner. This is a question where we're looking for an analytical solution. We're looking for M in terms of the quantities given here. So go ahead and take a picture of this so you don't have to sit there and copy it down right now. And I can put you into the groups. go ahead and create the groups now. Okay, the groups are open. Go ahead and join your breakout room. Anastasia, are you there? Anastasia, you there? Okay, I'm going to go ahead and stop recording. If you're watching on YouTube, go ahead and just pause the video. We'll be back in the blink of an eye. Go ahead and try the problem yourself. Okay, so those of you who are watching on YouTube, I forgot to resume the recording. We figured out the answer quickly to this question here for the Tesla coil, and we got mu0 n1 n2 a over the length of the solenoid 1. So I actually added a subscript here, L1. So double check with what you got. Then we talked about self-inductance here, which is essentially the same as mutual inductance, except just for one coil. So we just have one solenoid, and we use the letter L here when we're just talking about one solenoid. So self-inductance is the letter L. Mutual inductance between two solenoids, we use M. And then we talked a little bit about what we're headed towards, which is LR circuits. So one inductor, one resistor in series. We always make this assumption that ideal coils have zero resistance. Okay, so now we're looking at this problem here. Determine the self-inductance of a toroidal solenoid with cross-sectional area A and mean radius R. Closely wound with N turns of wire on a non-magnetic core. Assume that B is uniform across a cross-section. That is, neglect the variation of B with distance from the toroid axis. So essentially what they're saying is that inside this region here, the magnetic field is constant everywhere inside there. And what do they mean by the mean radius? They just mean the distance from the center to the center of the coils. Center of the torus to the center of the coils. Okay, so I'm going to go ahead and pause it again. Try this problem yourself. Wording. Okay. All right, we're back. So we're looking at this toroidal solenoid here, and we want to calculate the self-inductance. So in order to do that, we need to realize that we'll always start from Faraday's law, right? So minus L di dt. Okay, and this is equal to minus N d phi m dt. So this is our Faraday's law slash Faraday's law specifically for an inductor. Just go ahead and get rid of the subscript m here because we know we're talking about magnetic flux. And I want to drop the time derivative again. So that's usually like what we do when we look at these inductors. So if I drop the time derivatives on both sides, I end up with an expression like this. And we solve for L here. N phi over I. And then we substitute for phi is B times A. We can do this simple substitution of phi equals B times A because we're told to assume that the magnetic field is uniform across the cross-section of the torus. That's not true. If we had a solenoid, or if we had a torus that was quite large, we probably shouldn't make that assumption. But in this case, it looks fine because the size of the coil there is smaller than the radius of the torus. So we can go ahead and make that assumption. Let's not forget to divide this by I. And then let's substitute in what we were given here for the magnetic field of the torus, the toroidal solenoid. So N times mu 0 N I over 2 pi R. R is the mean radius. Let's not forget to divide by I, and let's not forget to multiply by A. And we see we'll get a little bit of a cancellation here. I's will cancel. I should always cancel for these materials which do not have a strong magnetic response. In other words, the magnetic permeability is a large number. So when the magnetic permeability is 1, or I guess I probably should say the, relative magnetic permeability, not the, because mu r, mu r times mu 0. So mu r is the relative permeability. So when the relative permeability is 1, then you don't have a strong magnetization of the material that you're putting the magnetic field in. When you have a strong magnetization, if it's like a ferromagnetic material, then some wacky stuff starts to happen. We're not going to worry about that though, because we're pretty much always building circuit wires and solenoids and things from copper, which is not ferromagnetic. All right, just let's clean this off real quick. So, or clean this problem up here. So mu 0 N squared A over 2 pi R, and the inductance does not depend on the current, which is nice. Okay, so that finishes that one off. Any questions about that before we go on to the next topic? You can give me a thumbs up. I don't know if you guys are doing it because I didn't have it up. You can give me a thumbs up if you're good on that. Okay, looks good. Let me get at, before we go to the next topic, maybe I'll ask another question here. So we looked at the mutual inductance. We looked at the mutual inductance between two coils. We did that right here, right? So we looked at mutual inductance between two coils, and we got this answer right here. M equals mu 0 N1 N2A over L1. Just based on the mutual inductance between two coils, what would you suspect for the self-inductance of a single coil? Let me go ahead and write that question out because I think that's something that you should think about. So what would you expect for the self-inductance of a single coil? And am I recording? I think I am, right? Yes, I am. Good. So if you're watching on YouTube, so just go ahead and pause the video here. I'm going to pause the recording to save time on the video so I can get it posted quicker. So try this question yourself. Okay, so we're back, and the answer to this question lies in the mutual inductance. What you have to do is you have to imagine that the coil has a mutual inductance with itself. Okay, so when the current is changing in the coil, the other coil, so to speak, is that coil itself. So in essence, it means that you have N1 is equal to N2 is equal to some N, which is just the number of turns of that single coil. So the self-inductance of a single solenoid, so a single coil of wire, so not two, just one coil of wire, so is mu 0 N squared A over L. Okay, so that's the self-inductance of a single coil. Okay, let's go ahead and go back to where we were before now. So we just got the self-inductance here for a toroidal solenoid, and now we're ready to move on to a new topic, of course related to what we've been talking about here, and that is energy stored in the magnetic field of an inductor. Okay. Energy stored in the magnetic field of an inductor. We'll just get a nice simple expression that should remind you of something like what we saw with capacitors. So let me remind you that first. So we found that the energy stored, notice this is a capital U, so this is energy, not energy density. So capital U for a capacitor was something like 1/2 C times delta V squared. Okay, so this is energy stored in a capacitor. Okay. And we were able to rearrange this, or rather substitute in for some of these quantities like the capacitance and the potential difference across the plates for a parallel plate capacitor where the plates are infinite. And we can write down an energy density for the electric field. And what we ended up with was 1/2 epsilon naught times the magnitude of the electric field squared. And of course, this assumes that the magnitude, that the electric field is uniform everywhere. When we did this substitution, when we went from the top expression to this bottom expression here, we assumed that the electric field was uniform everywhere. But actually, it turns out that this second equation is better than the first equation. This second equation applies even when the electric field is not uniform. And we can integrate this equation for a non-uniform electric field and get the total energy stored inside some region of space due to the electric field. So this, I would say, is energy density stored in the electric field. So we're going to follow that same kind of logic for the inductor here. Now we have to remember, how did we get that 1/2 C times delta V squared formula? And where you start is work, right? Or power. Let's start at power here. So power for any circuit element is the current that flows through that element times the potential difference across that element, right? That's by definition. This is like the definition of power right here. So definition of power for circuital elements, or just let's just say circuit elements here. But it's a little bit more general than that. And what we're going to do is we're going to replace delta V with what we've now understood as electromotive force, right? A lot of these things are induced electromotive forces that we're dealing with here. And so we're going to replace delta V with the EMF E, and then we're going to use Faraday's law. Faraday's law here, which is telling us that E is L times di dt. And you know what? Let me back up for a sec. Let's since we've been following the notation here, lowercase I for current this entire time. Let me go ahead and go back and change it to a lowercase I here. So we're looking at a situation where we can have the current vary with time, and so the book likes to use like the lowercase I, right? It's really just preference. It doesn't matter that much. There we go. So I've changed it to lowercase I. And so we've replaced the EMF with L di dt, right? Now I've dropped the minus sign because it depends, just like a capacitor, in what phase the inductor is going to be in, whether it's going to be supplying power to the circuit or whether it's going to be taking power away from the circuit. So let me give you the capacitor example so you have something to base what I'm saying on. So in one situation, the capacitor is being charged, and so it's taking energy away from the source. In another example, the capacitor could be discharging, and it would be supplying power, right? When the capacitor is discharging, that's power supplied. When the capacitor is charging up, that's power dissipated, right? Or really it's energy stored is what it is. Same case for the inductor. So we're going to have a situation where the inductor can be quote unquote being charged up, whatever that means. And then we can also have the reverse of that. So the inductor is quote unquote charged up, and now it's going to be discharging. But really what's going on there is it has to do with the change in flux. So, the flux will reach a maximum value and then it won't be changing anymore. And so then when the flux, starts decreasing or starts increasing, then it's going to be supplying, or it's going to be absorbing energy. Okay, so we'll be careful about that when we get there to really understand when it's doing what, but we're just not quite there yet. So I think you all have kind of seen what we need to do at this point. This equation has been on screen for quite some time now. L is constant, I is not constant, and we have a derivative with respect to T on our current here. And power we can always write as an amount of energy or work done per unit time T, right? So power by definition is the rate at which you do work, or the rate at which energy is dissipated, or the rate at which the energy is changing, right? So we can drop the time derivatives on both sides. Again, standard practice, right? So we have Li di is equal to dw, and we can integrate both sides of this equation. On the left, I have 1/2 Li squared. And on the right, I have the work done, or the energy that is needed. Let's go ahead and switch over. Or actually, we can write it in two lines. We can say, now this is the work that we do. And of course, the work that we do for this ideal inductor is going to be the energy stored. I use the letter U, actually. The energy stored in the inductor. So we use the symbol L for inductor, so the energy stored in L, the energy stored in the inductor. Okay, so 1/2 Li squared for energy stored in the inductor. Now that's a nice expression because it looks identical to 1/2 C times delta V squared, right? So it's kind of nice and kind of has that nice and simple form that we're used to kind of already seeing. 1/2 Li squared. Now, you could play around with this formula and write it in another form, maybe having to do with the magnetic flux. I think that in the case of an inductor, it's best to leave the formula as is, 1/2 Li squared. And if you don't know what I is, but you know what something else is, best to figure out what I is and then just plug into this formula. Because if we rewrite this formula kind of like we did with the capacitors, so if you remember for the capacitors, we had like 1/2 C delta V squared, right? And then we could change this. This is also equal to, Q squared over 2C, and we could also write it as 1/2 Q times delta V. We can do the same thing for the inductor, but it's just weird to do it. The formula is like it's going to involve magnetic flux and stuff like that. There's really no point in doing that. So we'll just leave it as 1/2 Li squared. And that's the one that we kind of want to remember. Okay, but there is one way that we should change the formula to get new insight, and that is to work towards an energy density which depends on the magnetic field. So what we want to do is we want to replace L and replace I. So replace L and replace I. Thankfully, I had you guys figure out what the inductor for a solenoid is. Let's go ahead and just assume that we have a solenoid. So let's make an assumption here and see what comes out of it. That's always the most difficult thing to do, right? Just to start a problem, make some sort of assumption that we're dealing with a solenoid. So we have a solenoid. Okay. That implies that the self-inductance is what? What's the self-inductance of a single solenoid? We just calculated that, right? That's mu 0 n squared times A over the length of the solenoid. So capital L here is the self-inductance, right? The lowercase l is the length of the solenoid. The next thing that we could do is determine the current, right? So if we have a solenoid, we know that the magnetic field is mu 0 lowercase n times I. Well, we could say I is changing with time, so we could have B is equal to mu 0 lowercase n I. The only thing I've done there is change to a lowercase I since the current is changing with time. I probably should say here we have an infinite solenoid, to be precise, because an infinite solenoid has only a magnetic field inside the solenoid. There is no magnetic field outside of the solenoid. If you guys remember that from, I believe that had been chapter 28, the chapter on Ampere's law. So now what do? Well, what we do is we take these expressions and we plug them into our equation for the energy stored in the solenoid. But if we just go in blind here, we're not going to get much out of it. So here's some modifications I'd like to make. So first, let's rewrite this equation here so that we have I equals. So I equals B over mu 0 lowercase n. And if you remember, lowercase n is big N over little l there, the curly L. So we have the current. So I'm going to box this one. I'm going to plug this one directly in. Now I want to work on this one next. I want to change capital N to lowercase n. So in order to do that, L mu 0, capital N is lowercase n times L. So I want to square that. You'll see why I'm doing this here in a second. So once I do that, what I have is mu 0 lowercase n squared, and I have an L squared, and I have an A, and I have division by L. So 1 power of L cancels here. And that's nice because L times A is the volume of the solenoid. So that's where we're going to get our energy density, right? So we have a volume here. We can divide the volume to the other side to get energy density. Okay, so let's finish it off here. So the equation that we're going to plug in is L equals mu 0 n squared times V. Okay, so we're gonna plug those in now. Let's do it right over here on the side so we can keep everything in plain sight here. So U equals 1/2 Li squared. That's the energy stored in the inductor due to the time varying current there. Maybe we'll use like purple or something to like substitute some of these quantities in. So the 1/2 stays. Maybe let's do this purple here for L. So L is mu0 n. And you, if you know what you're doing here, go ahead, plug this in yourself, get ahead of us. And then we'll use blue here for the current. So B over mu0 n, and we don't want to forget to square this one. Notice it's squared there. And we can see some cancellations happening. So n squared is going to cancel with that in there. What we're going to end up with is 1/2. I'm going to have a cancellation of a mu0. I'm going to end up with a mu0 in the denominator. Let's make that a little bit more explicit here. So 2 mu0 in the denominator, because I have mu0 squared here, and I have just 1 power of mu0 there. Okay, so mu0 in the denominator, b squared up top, and a volume up top. So we have b squared up top and a volume up top. And there we go. That is the energy stored in the volume of the solenoid where the magnetic field is. Only in the case of an infinite solenoid can we write this down. However, if we cleverly divide both sides by v, the volume, and we write lowercase u, we can say the energy density stored in the magnetic field anywhere in space is 1 over 2 mu0 b squared. And this formula it works in general. This formula works in all cases. So it doesn't matter if you have a toroidal solenoid, if you have a solenoid, you have a single loop of wire, you have an infinitely long wire with a magnetic field circulating around it, this formula works. So that's why we always divide both sides with a volume, because we end up with a formula that works in general. You can imagine a small volume, and if you make that volume small enough, the magnetic field is always uniform in that small region of space. And so that's why these formulas become more general when we talk about a density rather than the total energy stored there. So then if you wanted to know the energy in some region of space where the magnetic field varies with respect to time, then you would just say integrate b squared over that volume v, and that is how much energy is stored in space due to the magnetic field. Okay, and so now we've seen how energy is stored in the inductor. The energy is stored in the magnetic field, just like the energy in a capacitor is stored in the electric field. Okay, so any questions about that? Okay, so here's what we'll do. Let's go ahead and take a quick break. Let's do like our 10-minute break, because we've been going for about an hour and a half, so we're kind of like right at the midway point. We just finished a separate topic here, so probably a good idea to take like a 10-minute break, and then we'll come back at 7:55 p.m. and we'll do an example here, and we'll just keep going from there. Okay, so I'm going to go ahead and pause the recording. We'll be back in the blink of an eye if you're watching on YouTube. Okay, so we're back. We have an example problem here. The question is, the electric power industry would like to find efficient ways to store electrical energy generated during low demand hours to help meet customer requirements during high demand hours. Could a large inductor be used? What inductance would be needed to store 1 kilowatt hour of energy in a coil carrying a 200 amp current? So first things first, we're talking about energy, right? So let's go ahead and remind ourselves that the energy stored in an inductor, as we just saw, is 1/2 Li squared. Then we probably also need to remember what's meant by 1 kilowatt hour of energy. So 1 kilowatt hour, that's kilowatt is 1,000 watts, right? And an hour is 3,600 seconds, right? 60 seconds in a minute, 60 minutes in an hour. So 1 kilowatt hour, if you want to convert between the two, is 3.6 million joules, or megajoules if you like to use the prefixes. Okay, so I'm going to go ahead and pause the video again. Those of you who are watching on YouTube, pause the video so you have some time to work on this example. So I forgot to push record again. So what we need to do for this problem here is we simply convert the 1 kilowatt hour of energy into joules here, and then solve for L here. Maybe I should use another color here. So we're solving for L here. We get 2U over I squared. And then we are able to plug everything in. We have everything on the right-hand side. So 2 times 3.6 times 10 to the 6 joules over 2 amps squared. We end up with 180 henries. Henry is a special unit here. Henries are equal to joules per amps squared, also equal to volt second per ampere. There's many different ways you can write it, right? When we have these highly composite units, you can write it in many different ways. But we use Henry for the inductance, self-inductance and mutual inductance. Okay. All right, so let's go ahead and do the next topic then, if there are no questions here. So give me a thumbs up if you are good on this. Good to move forward. Let's see, where are we headed next? Next, we should be heading into RL circuits. It looks like we're good. That's almost everybody. Okay, so we'll go ahead and go into RL circuits. I think we're making good time here. We'll be able to cover all of the topics for this chapter. So RL circuit. What is an RL circuit? Well, an RL circuit is exactly what it sounds like. We have a source of potential difference. We have a resistor, and we have an inductor. Let me try and draw it nice and neat here for us. And later we'll talk about what happens when we add a capacitor into the mix. So here we have an RL circuit. This, I guess you could say, is a series RL circuit. Right, but once you know what to do for the simple series circuit, then you can apply that analysis to any complicated circuit with multiple series and parallel connections, right? Just need to go and do a little bit of extra work to figure out what the voltage is, for example, on a certain branch of the circuit or something like that. We may have time, I don't know how deep we'll be able to get into AC circuits. We may have time to look at some more complex circuits involving inductors, capacitors, and resistors, because that's when things get really interesting. You can have phenomena like resonance, wireless communications, and things like that via resonance circuits. Okay, so the RL series circuit, let's label some stuff here. So we have a resistor with resistance R, we have an inductor with inductance L, and we have a potential difference that's being supplied to the circuit, delta V. Let's go ahead and get some polarities labeled in here. We're definitely always going to have a voltage drop across the resistor, given by the direction of the current flow, right? So if current flows in this direction, I'll use a lowercase I here. If current flows in that direction, we're going to have a voltage drop across that resistor there. And now this is where things get a little opinionated, I would say, what to do with the quote unquote voltage drop across the inductor. Now, some physicists take the viewpoint that when you write down an equation for a circuit like this, which has self-inductance, that there is no voltage drop across the inductor because the inductor does not have resistance. And they assume that you need to apply Faraday's law in this case. And they say Kirchhoff's law is not good enough because Kirchhoff's law only works for electrostatics. You can't have magnetic fields going around. But I'm kind of the viewpoint of what is the simplest way to tackle the problem, right? And it works, and the physics is the same. Instead of applying Faraday's law, you apply Kirchhoff's voltage law, not in this form here. This is not Kirchhoff's voltage law. This is a statement about, this is, in essence, this is not Kirchhoff's voltage law. That's what I want to say. So we don't do this, but what we do is we sum all potential differences for all elements in the circuit. And of course, if we come back to our original starting location, we end up with a potential difference of 0, simply by the fact that, if you're going to define the potential at every point in the circuit, it's got to be a single valued object, right? You can't have multiple values for the same thing at one point. So it goes a little bit deeper than just potential theory in physics. It's more of like a mathematical reason. But yeah, so enough blabbering there. Maybe none of that even made sense to any of you. But we have a bunch of potential drops and gains in our circuit. And what we do is we just say, okay, we're going to have a potential drop across this inductor here. And even though it's a magnetic effect, it's not an electrical effect, it's a magnetic effect. Electricity and magnetism are one and the same thing. We have Faraday's law, right? So we're going to say there's a potential drop across this inductor here. Okay, so how do we do this? Well, we just write down what each of these potential differences is. So suppose I start right here at this point A, and I go around the circuit in this direction here like this, and I come back around to the point A. Well, then I would have gained a potential difference delta V. I would have lost a potential difference I times R. And I actually used the lowercase I. And I would have lost a potential difference minus a negative L di dt. As a matter of fact, actually, I probably shouldn't have a where's my eraser? There it is. I shouldn't put, there we go, like this. Yeah, so if we look at it this way, where I've drawn the polarity in this direction here, I'm looking at the magnitude. I've already chosen a direction here. So when I go through this derivation here of the current as a function of time, which is what we're after, and I chose this sign wrong, then what'll happen is I'll come out with a negative answer, right? If I end up with a negative answer, then I know I've chosen the polarity here incorrectly. But let's see what happens here and see that this choice is actually going to be the correct choice. So let's go ahead and take a look now. So we're dealing with a differential equation again, right? So not everybody has had differential equations, but this is a first order differential equation. So it's really not too bad here to solve this thing. I think the book even has a nice simple way of solving it, just separating variables. What I'll do to save time, because I don't want to spend too much time actually discussing differential equations, which is something you should just take a math class on, is I will make a guess as to what the current should be. And this guess is going to look very familiar to you. And you should be like, of course, it's going to have to be that way. Notice that if current is increasing in the circuit, for example, I have the circuit disconnected. If I put a switch, there's zero current in the circuit. And then I flip the switch. What's going to happen is the current is going to begin to increase. As the current increases, there is a magnetic field created in the solenoid there, the inductor, and that changes the flux through that coil of wire, and that induces a voltage which opposes that change in current, the increasing current. And so I think you can already see that my choice of the polarity of the voltage there is correct for the inductor. It has to oppose the increasing current. So it wants to drive current in the opposite direction. But eventually the current is going to reach a certain level. And as it reaches that level, it won't be changing anymore in the limit as for long times, right? In the limit as t goes to infinity, we can figure out what the max current is going to be. In fact, let's do that right now before I actually make my guess for I of t. If I take a limit on this equation, as t goes to 0, I know that eventually the current will not change anymore. And so what I'll have is delta V I max times R is equal to 0. So this term here becomes 0 in the limit. Does everybody follow the logic on that? Give me a thumbs up if you followed me on that. So in the long time limit, after a long amount of time passes, the current is going to be steady. It's not going to change anymore. So di dt would be 0. If you have a constant current, the derivative is 0. Okay, so that tells us right away that the max current flow in the circuit is just like what it was for the capacitor before. It's delta V over R, right? Delta V over R is going to be the steady state, the maximum current. In this case, it's a steady state current. So that is a difference. In the case where you're charging up a capacitor, when you charge up a capacitor, eventually the current is 0, right? So you start at a maximum current, you go down to 0. For the case of an inductor, the current increases from 0 and it reaches a peak value. I call it I max here. And that's going to be delta V over R. All right, now let's make our guess here. Let's do the guess in blue here. So here's our guess. Now you're probably, if you've never taken a differential equations class, you're probably like, why are we guessing, right? There's got to be an analytical way to do this. Actually, making a guess is a very rigorous way of solving a differential equation. And oftentimes, if you make a wrong guess, you've made a certain guess, and in going through the process of checking to see if your guess is correct or incorrect, you gain some knowledge which helps you refine your guess, and then you can go back in and do it again. And eventually, as you refine your guess a few times, and this is actually a standard practice in like some nonlinear, not nonlinear, but like partial differential equations. You make a couple guesses, and eventually your guess is refined enough. It's like, okay, now I have the general solution. But here for a simple first order equation, it's pretty obvious. We have the derivative and we have the function itself. We have I and we have the derivative of I. It's got to be some kind of exponential. So let's make a guess, I max. And we said that the current is going to start at 0 and it's going to go up to a maximum value. Well, if you remember, that looks like this, our friendly exponential function, 1 minus e over tau. okay? And it's up to us to figure out what tau is. I'll leave it to you to actually plug this back into the equation and see that it solves the equation when tau is equal to L over R. And again, you can check that Henries divided by ohms have units of seconds. Henries divided by ohms have units of seconds. Okay. So if we plug this back in, we're gonna see that this is the solution, and that is for something for you all to do. We're not gonna go through that right now in class. Do it yourself. Verify that that's true when tau equals L over R. Okay, the next thing to do would then be, of course, now we have the current. So now we want to figure everything else out, right? We want to know what's the voltage drop on the resistor, right? Okay, that's I times R. What's the voltage induced in the inductor? Okay, that's minus L, or actually, since we've already chosen the direction, we can just look at the magnitude. That's going to be L times di dt, right? And so forth. There's no Q in this problem. There's no charge being built up on a capacitor. So there's no Q that we deal with here. So LR circuits, in a sense, are slightly less complicated than RC circuits. Let's just go ahead and figure those things out right now. So delta VR as a function of t is simply I of t times R, which of course is going to be I max times R times 1 minus e to the minus t over tau. So the voltage across the resistor eventually reaches a maximum value when the steady state current is flowing. Furthermore, we have the potential difference across the inductor, and I will use the symbol delta V sub L because when we're doing circuits, we're often using delta V's for different batteries and things. But of course, you could use the symbol E if you want to. If you want to write E of T here, that's fine. I just like to sort things out with the subscript. So everything is a delta V, and I put a subscript for the resistor. Maybe it's R1, maybe there's an R2 as well. Maybe there's an L1 and an L2, so I put delta V L1, delta V L2, and so forth. That's up to you, right? However you want, however you're comfortable with. So in this case, we have L times di dt, and L times I max, which is constant, times the derivative of this function here. So we want the derivative of this function right here. We can see that there's a minus sign here, but chain rule is going to give us another minus sign. Excuse me. And so we're going to get a net positive here, and we're going to end up with e to the minus t over tau. So double check that derivative. Make sure that what I'm saying is correct here. So L times I max e to the minus t over tau there. And again, you can look at this equation in another way. You can say, of course, I max is delta V over R, right? So if I write this as I max is delta V over R, I have L times delta V divided by R times e to the minus t over tau. And then I can make one more change. I can say, hey, look, I have L over R here. L over R is tau. So I can say tau times delta V e to the minus t over tau. Right? There's numerous different ways to write these expressions. For example, the voltage drop across the resistor. I don't have to write it as I max times R. I can write it as delta V, which is the source voltage, the voltage that's being supplied to the circuit. So, 1 minus e to the minus t over tau, right? There's many different ways to write these things. Again, you always want to be thinking about what's going on in the circuit. So the current must be increasing to some steady state value when you have an inductor and a resistor. The reason is because the inductor is not storing any charge, right? The inductor is not storing any charge. So the current is not going to eventually go to zero. Eventually, the inductor is going to have no effect on the circuit because it requires change. In order for the inductor to have an effect, you must have change. So when I flip the switch on my circuit, there's change, right? But eventually, conservation of energy, right? There's not going to be change forever. Eventually, this thing is going to taper off to a maximum value. So this is your 1 minus e to the minus t over tau function. This axis here is t. And this is the 1 minus e to the negative t over tau axis. And of course, then we also have the e to the minus t over tau function. And we have the t-axis here as well. Okay, so that said, it's the same mathematical functions because the differential equation is identical to the one we had before, except we've replaced q with I. We used to have q and dq dt. Now we have I and di dt. When we go to an LRC circuit, which is actually in this chapter, it's the end of this chapter, we will have a second order differential equation, okay? And then things will be slightly more complicated, but not that much more complicated. Okay, let's look at an example here. So we kind of need to ration out the rest of our time here. We have about 40 minutes, so hopefully we can get some decent examples done here. So let's see here. Yeah, we can go ahead and do this example here. And let me save us some time. I'm actually just going to copy the question over. What happened here? I don't know what happened there. I just lost the question somehow. Okay, here we go. So here's the question. And I can zoom in on the question. There's no figure for this question. I can zoom in on it. And it's a little bit less blurry than if I drag it and make it bigger. So maybe this is good here for you guys. So this is the example. I'll read it one time. A sensitive electronic device of resistance 175 ohms is connected to a source of EMF, so a source voltage like a battery, by a switch. The device is designed to operate with a 36 milliamp current, but to avoid damage to the device, the current can rise to no more than 4.9 milliamps in the first 58 microseconds after the switch is closed. An inductor is therefore connected in series with the device. It's the same, it's just a series RL circuit that we just saw above. The switch in question, S1, blah, 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 right? What is required, what is the required source EMF? E, and what is the required inductance? What is the RL time constant tau? Okay, so we have a simple series circuit. I'll go ahead and draw it for you. It looks like this. Okay, exactly what we just saw. R and L. And this is our applied voltage delta V here, or actually they do use the symbol E here. They do use the symbol E, but if you want to use delta V, that's fine. Everything is the same. So they tell us the current can rise to no more than 4.9 milliamps in the first 58 microseconds after the switch is closed, okay? So I'll give you some time to work on that one. I'm going to pause the recording. Okay, so we're back. Let's quickly discuss parts A, B, and C here. What is the required source EMF in order to get this device operating at 36 milliamps of current? Well, we have to apply Ohm's law, right? So Ohm's law says the EMF is going to be the current times the resistance. And if the device is operating, then the current that we want to use here is what we called I max before, because that's going to be the steady state current. That's going to be the current after a long time. The device needs that current to continue operating. So that's going to be our 36 milliamps there. So 0.036 amps times the resistance of the device, 175 ohms. And we end up with about 6.3 volts there for that. That's part A there. That's the EMF that we need to run this device. Now, of course, when we plug this device in, we have self-inductance here in the circuit. And the reason we've got to account for this self-inductance is because the current starts at 0 when the thing is not plugged in, and then it jumps up to a certain value. That's not realistic. We need to have a continuous current. It will increase up to the steady state value. So part B deals with the required inductance. We're told that the current can't rise any more than 4.9 milliamps in the first 58 microseconds. Maybe it's going to damage one of the components if the current jumps up too quickly. Okay, so in order to do that, that's basically like solving for the inductance from the time constant. Okay, so what we want to do here is we want to say that the current as a function of time is equal to I max times 1 minus e to the minus t over tau. And we can take a ratio here. I'm going to slide on over to the side here. Maybe come up over here. 4.9 milliamps is our maximum current that we can have in a time of 58 microseconds. So I'm going to set this up as 4.9 milliamps is going to be equal to, as I'm going to actually, you know what, let's actually not do that just quite yet. Let's first solve for tau in general. In order to solve for tau here in general, what we need to do is we need to go I of t over I max. We can subtract the 1 over, and we can multiply both sides by a negative, and we can take the natural log. I know I'm going fast on the algebra here, but just bear with me on it. Multiply both sides by a negative, take the natural log on both sides, and what we end up with is minus t over tau. So you can check what you did for this problem to see if this is still correct for you. And then we can go ahead and plug stuff in. So maybe actually I still would multiply tau to this side, and I would move this to the denominator over here like this. Okay. And then I would plug in, okay, t is equal to 56 or 58 times 10 to the minus 6 seconds. And my I of t would be equal to 4.9 milliamps. And we plug all of this in here. Let me not spend time calculating it here. The answer is right over here. For this example, we end up with 690, or sorry, is it 69 millihenries? 69 millihenries for L. So tau is L over R. So we have to multiply this thing by R as well. And R is 175 ohms, right? Yeah, 175 ohms. Okay, so we end up with L is 69 millihenries. So you can maybe put in the chat yes or no if you got that answer there for that one. That one's a little bit of a long-winded one there. And once you have L, you can calculate tau as L over R. You get 390 microseconds. Any questions about that one? Give me a thumbs up if you're ready to move on to the LC circuit. All right, let's go ahead and move on to LC circuits now. I'll go ahead and zoom out. I have some stuff already written here. Let's kind of go through it a little bit quicker so we can save a little bit of time. We want to get into LRC circuit before we get into AC circuits. So we really want to get through this. Here's our circuit here. We have a capacitor up top, an inductor on the bottom, no voltage source, no battery in this circuit, okay? Could we have a battery in this circuit? Yes, we could, if we want to. We definitely could. If we had a battery in this circuit, what would happen? Well, the capacitor would eventually become fully charged and no current would flow in the circuit if we had a battery in this circuit. However, something interesting happens if you start with a charged capacitor and so let's say you connect the capacitor to a voltage source, you charge it up, then you disconnect the battery. Now the capacitor has charge and that charge begins to discharge to the inductor and a current begins to flow. And because that current begins flowing, you induce a current in the inductor, which opposes that change and fights against the discharging of the capacitor. Here in this circuit with no resistor, energy will be exchanged until infinity. The circuit will continuously oscillate between charging and discharging the capacitor due to induction because there's no resistor. If we put a resistor in there, that won't happen. We can see that by applying Kirchhoff's voltage law. The voltage across the capacitor minus the voltage across the inductor has to equal 0. Then we substitute in what these quantities are. The voltage across a capacitor, that's actually a mistake there. The voltage across a capacitor is its charge divided by its capacitance. Q equals CV. Q equals C times delta V. And if we solve this for delta V, we see delta V is Q over C. And so we've plugged that in here with a lowercase q because it varies with time. For the inductor, we have the voltage across the inductor given by Faraday's law, or the version of Faraday's law with this self-inductance term, L times di dt. The polarity of the voltage across the inductor is always opposite to the polarity across the capacitor. And di dt, of course, is the same as the rate of change of dq dt. Current is dq dt. I, by definition, is dq dt here. And so the second derivative of the charge comes into play here. And it looks like I forgot a 2 right here in the denominator. So it's second derivative of q with respect to time there. So since we have a second derivative, we have what's called a second order differential equation, which is a little bit more challenging to solve than a first order differential equation, but not too much harder because we have seen this one before. Presumably you've seen this equation last semester in the form of a mass on a spring. Okay, and they go into the details on that in the textbook. In this chapter, they say, oh, look, but this is just like an equation we already have seen before. And they say, okay, well, the solution for a mass on a spring is a cosine. We can do that here as well. So we can say, all right, if the capacitor starts out with some amount of charge on it, then we can guess that the charge on the capacitor is going to go like some amplitude times a cosine of something, let's say omega t, plus some phase angle here, phi. This is phi, a phase angle. It has nothing to do with flux. And we're going to set the phase angle equal to 0 here. And the initial amount of charge at t equals 0, excuse me, let's write this properly here. So Q at t equals 0, we're going to call that the initial charge, Q0. Okay. So these are our initial conditions here. The charge is going to begin at a maximum value Q0. That's ultimately going to lead to the fact that the phase angle here is 0, and it's ultimately going to lead to the fact that A is equal to Q0 there. So go and follow the logic there for yourself and make sure that that makes sense to you. And so Q of t is going to be an oscillating function, a cosine function, Q0 cosine omega t. Okay, just like we would see for a mass bobbing up and down on a spring as it hangs under the influence of gravity. Okay, from that we can figure out what the current is going to be, we can figure out what the voltage across the inductor is going to be, and so forth. It's not difficult to do, we just need to take a derivative here. If we take the derivative dq dt, of course we pick up a minus sign, minus Q0 omega cosine omega t, right? And this of course is the current as a function of time here. Okay, that is the current as a function of time. And any questions up to this point? I know I'm going a little bit fast, so let's maybe slow down for a second. Any questions at this point? So we do have a chat here. Isn't it sine omega t? It depends. It depends on your initial condition. So if we're going to say that the capacitor starts with an amount of charge Q0, and that is the maximum amount of charge. So this is the max amount of charge, then it has to be cosine, right? Because if I plug in t equals 0 here, look in red, I'll write it in red here. If I plug in t equals 0, then the cosine is 1, right? If the cosine is 1, then I recover at t equals 0, Q0, right? Now, if I plug in, let's say, omega t equals 90 degrees, right? I'm a quarter of a period later, then I would see that the charge on the capacitor is 0, right? Because it's a cosine. So it begins at a max and it will go down to 0, and then it will begin to go to the opposite charge. So the polarity on the plates will change from minus plus to plus minus. Okay, so it is a sign. It's definitely a sign based on our initial condition here. We could take an initial condition that the charge on the capacitor is initially 0, but the magnetic field or the current flowing in the inductor is initially at a maximum value. That's another initial condition that we could take. You're free to make that your initial condition, right? And maybe there's a problem on the homework where that is the initial condition. And so that will slightly change things. That will end up shifting the cosine here to a sine. And then for the current, I totally made a mistake here, by the way. Maybe this is what you were talking about, Lick. Maybe I'm rambling on. I'm just not even understanding your question. You probably meant that this was a sine, didn't you? My bad on that. So this is a sine. Yeah, this is definitely sine omega t here. So I guess I just didn't understand the question. Sorry about that. So let's plot that over that cosine there. My bad on that one. So yeah, it is minus Q0 omega sine omega t. Yes, good catch on that. I'm surprised nobody said anything. I've been rambling on, and I just completely misinterpreted the question there. So yeah, sine omega t for that case there, yeah. Now we can go about calculating the voltage across the inductor, the voltage across the capacitor if we want to, but this is basically where everything comes from. Once we have Q of t, we can get everything else. Now there's an obvious question here. There is a symbol here in all of these expressions that we have no idea what it is yet. We have no idea what it is yet, and that's omega, right? What is omega, and how do we figure out what omega is? How do we figure out what omega is? right? So how do we figure out what omega is? Of course, omega has units of 1/seconds, right? Omega has units of 1/seconds. The best way to determine what omega is going to be is to consider the case of a spring, okay? Consider the case of a mass on a spring. For a mass on a spring, the second derivative of the position with respect to time plus k/m times the position measured from equilibrium equals 0. This is the differential equation which describes the oscillations of a mass on the end of a spring. Now, the quantity omega in this case is the square root of this thing right here. So omega is the square root of k/m. What would that be in our case? So we have to go back and we have to look at our differential equation here. We have right here, we have this L right here. We should divide this thing to the other side. So we should put the L over here and cancel the L. And then we can see that the term with no derivative is multiplied by omega squared. So 1/LC is equal to omega squared. So for us, omega squared is equal to 1/LC. Therefore, omega is the square root of 1/LC. You could take the plus or minus sign, but usually we define the frequency to be a positive number. It's the number of times something repeats in 1 second, right? In this case, this is an angular frequency, so we multiply the frequency by 2 pi. Okay, so this is what we call the resonance frequency for this circuit here. So resonance frequency, or rather resonance angular frequency. So if you want the resonance frequency, you can divide this thing by 2 pi. So the resonance frequency is 1/2 pi, 1/LC under a square root there. Okay. Now, what good is knowing this resonance frequency? Well, the resonance frequency, as we're going to see moving forward, and this is probably in the chapter on AC circuits, so I'm not going to get into too many details here. You're going to see that maximum power is going to have something to do with resonance frequency, and that kind of makes sense, right? When something is resonating, that means it's operating at that frequency that is best. It's kind of like that's the frequency you've designed your system to operate at with the most efficiency, so to speak. So that's how the resonance frequency is going to come into play. Okay, so you can also set up circuits where you have a mutual inductance between two circuits, right? You connect 2 coils of wire. You overlap 2 coils of wire, and you have one connected to a circuit and the other one connected to some other circuit. And you're going to have resonance. You're going to set the circuit up so that you're in resonance, so that you transfer maximum power from one coil of wire into the other coil of wire. You're going to minimize the loss. So that's super important when you're dealing with power lines, which power lines, by the way, use these nested coils. They're called transformers. When you put one coil inside of another coil and you have a mutual inductance between those coils, and so you transmit the power from one coil into another coil, and you can actually design those transformers to increase voltage or to decrease voltage. So what happens in power lines is you're dealing with hundreds of thousands of volts or maybe tens of thousands of volts closer to the city. And then you use transformers to lower those hundreds to tens of thousands to thousands, all the way down to 120 volts that you get in your house. And as that voltage decreases, it's going through this transformer. These are the boxes. If you look up at the power lines, every 5 power line towers or so, you'll see one of these power lines. It'll have like a box up there. Inside that box is this really massive transformer that decreases the voltage from tens of thousands of volts down to, some 100 volts or something, 120 volts. Okay. Let's go ahead and move to RLC circuit now, the full-blown circuit. And this would be where we'll stop. And we'll do a lot more on RLC circuits in the next chapter when we talk about AC circuits. So it's kind of a small section here, but I definitely want to cover it. This is actually one of the more once you get into AC circuits, everything starts to get a little bit more interesting, because you're doing all these problems and like with differential equations and stuff. And then all of a sudden you get to AC circuits, and yeah, you can set up some differential equations, but there's a nice thing that we can do that makes everything so much simpler when we're dealing with AC circuits. So it's really nice. So let's go ahead and we'll scroll down here. I've given you plenty of time to write that down. We'll look at RLC circuits. Now, I think in your book, they write the letters in a different order. Who cares, right? If it's LRC circuits or CRL circuits, doesn't matter. So we're looking at RLC circuits. Now, these are circuits where if you're dealing with a circuit where you have a constant voltage source in your circuit, again, the capacitor will become fully charged. And because the capacitor becomes fully charged, there's no longer any current running in your circuit, right? And so what we're going to look at is, again, a simple series RLC circuit where the capacitor is already charged. The book will show you a figure where it has a switch, so the capacitor is charged up first, and then the switch is flipped, and then it's a circuit with a capacitor, inductor, and a resistor. Let's just cut to the chase here. We have a capacitor that's already charged. We have the inductor here, and we have the resistor here, like so. So we have capacitance C, we have resistance R, and we have inductance L. And suppose the capacitor is charged in this fashion here. So we'll have, it's not positive on both sides. It's negative on one side, positive on the other. And so there's going to be a voltage drop across the resistor like this. And we can assume maybe the voltage drop is going to be like this if we initially start the capacitor at full charge, so the current is 0, and then we allow the capacitor to discharge. The voltage drop is going to be in this polarity here across the inductor. So we have Q of t for the capacitor. We have I flowing through the resistor here. And of course, we have I as a function of t, right? To set up the Kirchhoff's laws for this circuit here, the Kirchhoff's voltage law here for this circuit, sum all the potentials equal to 0. What we have is Q of t over C for the capacitor, minus I of t times the resistor, resistance of the resistor R, minus L di dt. And now we can see we definitely have a second order differential equation here. So it's getting a little bit complicated now, right? Now we have Q, we have dq dt, and we have second derivative of Q with respect to t. So let's go ahead and illuminate that. So we'll write all the derivatives out here. And I know we have 1 minute left, so I'm going a little bit faster, but of course we're recording this, right? Am I recording right now? Yes, I'm recording. So you'll always be able to go and watch it again, right? So now we have dq dt with R there still. Current is dq dt, and then minus L, second derivative of Q with respect to t here. So if we want to solve this equation, what we have to do is we have to make a guess, and we have to impose an initial condition here on this thing. What I'll do is I will cut to the chase on this one, because this particular differential equation leads to a rather complicated solution. So deriving a full solution to this equation is a little bit more involved than simply guessing an exponential or guessing a trig, guessing a cosine, or guessing a sine. And the reason for that is because, so suppose if we just had this term and this term, it would be an exponential. If we just had this term and this term, it would be a sine or a cosine. But since we have all three of these terms, there's a chance that it's a combination of an exponential and a trig function. And what do I mean by combination? I mean multiplication of those two things. Okay, so that happens to be the case in this situation. So what I would do normally is I would divide through by L here in this equation. I would divide through by L. So we have an L here, and we have an L in the denominator there. So that way the leading term here, and I would divide by a minus sign as well. So that way the leading derivative, the highest order derivative, is a constant 1 out in front. And then I would go about applying some method of solution from a differential equations class. So it is possible to do this question by making a guess first. But when you make your guess, you better leave yourself a function of t undetermined. So what you can do, if you're interested in solving this equation here, there's a nice little method you can do. You can say, let q of t be some function of t times some exponential. And for this exponential, maybe you say minus a times t or something like that, where a is just some constant. Okay, and so when you plop this in there, you will be able to figure out that, okay, the exponential piece, you can manipulate this so that the exponential piece kind of comes out when a is a certain value, and then the f of t is left over. There's another differential equation you can solve for f of t. That's one method of doing it. There's another method of doing it. You could guess two exponentials or something and then use, what is it called, like Abel's method to get the general solution or something. But yeah, it's just a little bit too complicated for us. So we're going to not do this. We're going to just go straight to the solution given in the book here. So it's some initial value, e to the minus r over 2l times t. And this r over 2l is not a time constant for this circuit, because we have another function of time multiplying this thing, and it's kind of a nasty one. Cosine of 1 over LC. Oh, whoops, sorry. That doesn't end there. 1 over LC minus r squared over 4 L squared, and then times t on the outside of this root here, plus some phase angle phi, which you can usually set that phase angle to 0. For example, if I say at t equals 0, the charge q is, let's say, q0, that's the maximum amount of charge in my circuit, then I can get rid of the phi here. I can make that 0, because the cosine will be 1 when we have maximum charge, and the exponential here will be 1 when we have maximum charge, which tells us that A here would be equal to Q0. Whatever the initial charge is on that capacitor, that's the maximum charge that will ever be there. Okay, and this term right here is, again, our angular frequency, which you would figure this out. You would figure this out by drawing analogy with the damped harmonic oscillator. So that's another way you could solve this equation. You could think about this equation as being an analogy with a damped harmonic oscillator, and you could go back and look at the damped harmonic oscillator solution and match the terms, right? So this is our angular resonance frequency, so to speak, except here's the thing. We now have a resistor in this problem. So the capacitor will eventually reach zero charge, and it will be zero forever after, because the circuit has a finite amount of energy, and all of that energy will be dissipated by the resistor eventually. Okay, so from Q of t, I'll leave it as an exercise for you to find out what is I of t, right? What are the V of t's and so forth. And yeah, David mentions Laplace transforms, which is a nice method of solution for a problem like this. Whatever method you want to employ. If you want to use like a Green's function method, that's probably the most fun way to do it. Integrate this thing in the complex plane and use the residue theorem. But probably none of you even know what I'm talking about, so maybe I shouldn't even mention that. So yeah, so that's the idea here. There's an example in the book, super simple example. They don't even really have you do anything with these equations here, the Q of t and so forth. And the reason why is because when we have a circuit like this, where there's no AC source, things are rather complicated. Okay, things are rather complicated here. This is a nasty looking function. And this will greatly simplify when we have a voltage source, an EMF, which is some sort of sine. Let's not use A. Let's just throw it in there, omega band, right? Omega band. When we have some sort of sinusoidal voltage source, everything simplifies so much for RLC circuits. So this whole nasty thing with this differential equation here, that doesn't even exist in AC circuits. Well, it exists, but the solution to it is much easier. And the reason is because when we have a source which is alternating, we can define a quantity called impedance. And impedance is like resistance. In fact, it is resistance for a resistor. Impedance is the resistance for a resistor. But impedance allows us to define a term which is like resistance for capacitors and inductors. So it basically reduces everything, all this complicated stuff with these functions of time, into an Ohm's law expression for capacitors and inductors. So it makes everything super simple, right? So in a physics class, we love doing everything the complicated way and then introducing the easy way after we do it the complicated way, right? So you learn kinematics, and then you learn dynamics with forces and everything, right? And then you learn like complicated stuff like the line integral, path integrals for work. And then finally you get to energy, right? And then you have the work energy theorem. So you have conservation of energy. And then you solve all those old problems nice and easy again with algebra instead of calculus, right? And the same thing for like conservation of momentum as well, right? So you can't deal with collision problems until you use Newton's third law to prove that you have conservation of momentum and move from there. So again, algebra, right? So we go from calculus to algebra for some reason. Same thing is going to happen here, right? So we're doing all this complicated calculus. And then when we get to actually the chapter on AC circuits, everything is going to reduce back down to algebra. And as a matter of fact, it's even cooler than that because it reduces to algebra in the complex plane. So if you're looking for something to do over the Thanksgiving break, besides the few assignments that are posted, review your complex numbers. Okay, that's where we're going to end it. Any questions? Let me know if I gave too much homework on the assignments for this week, because I was really trying to cut it down a little bit because of the break. I don't want to have you guys do a bunch of work over the break. But if you need to do the work over the break, let me know and I can extend those for you. I can extend those assignments for you. Okay, so we're done now. So I'm going to end the recording so you guys can ask me any questions.